Next, we'll consider short space problem, and this one is called stagecoach problem. It's published in Wagner, which is a prominent researcher in operation research in the textbook. Okay, we start from A, and initially we have three choices, and this is the second stage, third stage, and fourth, and we reach the destination. So how could we find the shortest path from the origin to the destination? So the idea is one step. We call it a principle of optimality. We have multiple stages to go through. So we decompose the big problem into one step and cost to go. So from here, we have a one step 2, and from B to the destination is called cost to go. And the other choice is go through the middle point. The distance is 4, and this is cost to go. And finally, the third path is this low one with a distance of 3 and cost to go. But we don't know the value of f of d, so we start from the end. So this is called principle of optimality, one step and cost to go. We will see a lot this kind of approach. And this is the fundamental idea of reinforcement learning. So this is our initial condition. F of h is 3, f of I is 4. And the next one is f of e. We have two choices, right? One is one step, cost to go. And the second one is 4, cost to go. So we choose the minimum one, which is 4. And you repeat the computation of f of f here and of f of g. So the next way is f of b, c, d. And at this stage, we have three choices here, which is 7, 4, 6 for one step and cost to go. And we choose the minimum one. And finally, for the origin. As you can see, we reduce. Okay, this is, we try to compute, right? But when we try to compute cost to go, we don't need to repeat this process. So it will reduce the computational time, which is why dynamic programming is a more efficient than exhaustive solution. And we'll see that in the later PowerPoint. So you don't need to compute again here, and also for this part and for this part. Okay, and for the final stage, you don't need to repeatedly compute f of b, c, and d because you have the solution here. So for shortest path, we could find 3 optimal solutions with cost of 11. So we have 3 choices here. For myopic policy, we choose the shortest path starting from A. So from here, we 2, 4, 3. We choose this one, and we choose 4, right? And next one, we choose 3, and final is 4. So the total cost is 13, right? 2, 4, 3, 4, which is larger than the optimal path. As you can see, because we start from the end, our destination, so in the middle stage, we might go to a longer process here. A of d, AD is 3 instead of 2. This is myopic, right? And this is the optimal path. Because we look at the global picture, we try to find the minima So in the middle stage, we might sacrifice a little bit so that we could reach the final destination with shorter path. As you can see here, if for the myopic policy, you go here from here, if this cost is 10,000, then the total cost is much larger. So it's a famous quote. It's called "Chance favors prepared mind," which means that you could think of this as a career choice. For example, this is your final goal, to be a manager or to be a professor. So in the process, you need to do something. For example, improve your communication skill, take some courses, or get a PhD. So it is sometimes it is hard work, but in the end, you could reach your goal. The other one is computational complexity. I think this one is very important, and it's a fundamental idea in computer science. Actually, they introduced this kind of course in data structure or algorithm. It's called Big O. We try to compute or compare time and space complexity, and this is the origin of the notation, which is a long time ago. And O is a means ordinate, means order of approximation. And this is the expression about this one. If there exists positive real number m such that this one holds in the domain, so we'll give you an example, f of x. This is the function. And we try to compute its upper bound. So this one is less than 1 because we choose absolute value from algebra. And this is -1, so we change it so that we become a positive 1. And also for x greater than or equal to 1, x the power of 3 is always less than x to the power of 4. This is an upper bound, right? Finally, we add the coefficient together, we get 13. So in terms of big O, f of x is on order of x to the power of 4. In this case, you could choose the most important one. That is, when x is big, this term will dominate. This is the basic idea. We try to find an upper bound. However, if you choose your upper bound with power of 10, it's less precise, right? Because this one is much larger than x4 when x is very large. So we need to choose the exact, the most important one. In this case is x to the power of 4. So we'll compare the complexity of two algorithms. The first one is brute force. You don't have any training. You just use your intuition. That is, you find all possible paths and compute the optimal one. This is called brute force. So how many paths we have? Because assume we have a middle layer instead of 2, and each with 3 nodes. So initially we have one path, and for each stage there are 3 choices. So it's 3 to the power of n, and this one, the second to the end, is 2, and finally it's 1. So this is the path we have. And time complexity, they are actually from the previous example, right? You can see there are 2 operations in addition, and one is comparison. So you need to compute these 2 operations. For addition, there are n plus 2h, each require n plus 1 addition. So this is our total path right here, total path. And this is addition we need. So its complexity is n times 3 to the power of n. In comparison, we need to find single minimum value upon all total path. So this is our path, -1. So we choose the dominant one, right? So this one is dominant, which is much larger than this one when m is big. Remember, we are dealing with large problem. So this one is our time complexity. For space complexity, we generate sequentially, so we only need to store the minimum one under evaluation. So this is our space complexity, constant in space. So for brute force, it will take exponentially time to compute the optimal path. On the other one is dynamic programming, backward stage by stage to solve local transition. So from two node layer to destination, we have 2 addition, right? 2. From less 3 node layer to the 2 node, we have 6 addition and 3 comparison because we have 3 node. And within the n layer, and this is addition for each node. We have 3 nodes, right? For each node, we have 3 addition, so it's 9 addition, and we have n-1 layer. And this is from origin to the first 3 layer. So this is our total addition, and you could compute comparison accordingly. So it's time complexity here is linear. N is the stage number, which means that when the stage grow bigger, the time compressed is linear. However, for brute force, it's exponential. Okay, so you see the merit or importance of a great algorithm to solve real-world problem. And we will see other example in scheduling. We will encounter very difficult industrial problem. So time complexity or space complexity is very important, even for industrial engineer. And we also consider space complexity, and we compute the minimum value, and if we tracking the full routing path, so this is our space complexity, which is not bad, it's still linear.